thank Olivia for inviting me to this conference. When she did, I realized I have it occurred to me to give myself two exercises. The first is to formulate some question, but formulate precisely some question that bridges geometry and number theory. And the second exercise is to muse about the title of this conference, Unifying Themes in Geometry. So the question I began with was a little broader than geometry. What unifies mathematics? And I should say that I have asked this question in different formats. And for an account of my attempts at thinking about this, take a look at my webpage. So the natural question is, what is it that unifies mathematics or geometry? But before you ask that question, you might ask, what is mathematics? A friend of mine, a physicist, says that anything a physicist labels as physics is physics. As for biologists, life is a single word that points to the unification of their subject. For example, from proteins to the behavior of elephants to medical applications, etc. So what's the unifying anchor for mathematics, or perhaps just for geometry? Is geometry unified? Does it matter? And are there useful ways to think about these questions? Well, we have one of our many founding documents, and that's Euclid's Elements of Geometry. It's supposed to be a founding treatise for geometry, and it does end quite nicely with the construction of the regular Platonic solids. But even in this foundational book, the tentacles of our subject, geometry, they reach out, for example, to number theory, as in Euclid's Book 6. And here are the definitions 11 and 12 in Book 6. I'm giving you Heath's English translation, which has a kind of antiquated flavor. A prime number is that which is measured by a unit alone, an unit alone, and composite numbers prime to one another, are those which are measured by an unit alone as a common measure. But once you've made these definitions, geometric language enters Euclid's elements. For example, composite numbers are called plane numbers. Numbers that are products of three factors are called solids. I keep wondering what Euclid would think of a number that's a product of four factors, but the factors of these three are called sides. So there's a kind of geometric attempt to organize number theory. On the other hand, when you get to Book 9 of Euclid, you discover his marvelous proof that there are infinitely many primes, and I've put it in that quotation there in English and Heath's English. It's a very vintage English. If you haven't read Euclid's Elements in translation, in English translation recently, do. It's quite amusing. Now, there are other ways in which geometry connects to subjects besides making planes and solids. My current favorite examples are these two in these bullets. Pfefferman uses geometry. He uses the solution of that amazing Kakaya needle problem to give a beautiful characterization of the L2 norm among all LP norms. And going the other way, Marina Biazovska uses number theory, or mock modular forms, if you want, to solve a geometric problem, the sphere packing problem, dimension 8 and dimension 24. So geometry does connect in various ways. Nowadays, topology and physics are companions, at least a certain type of mathematical physics. And I think the thrust of this was started, or at least nudged significantly by Michael Atiyah, who asked a very simple question: what is the physical interpretation of the Jones polynomial? And the answer is there was a physical interpretation, and Ed Witten gave it in his quantum field theory and Jones polynomial, a famous fundamental paper that began a whole discipline almost. So we can follow Atiyah and we can ask pretty much the same question, but instead of saying, what is the physical interpretation, you might ask, what is the number theoretic interpretation of the Jones polynomial? That is, say, the arithmetical, algebraic, geometric interpretation of the Jones polynomial, or of Chern-Simon's theory, or the topological quantum field theory, for example. Now, much current work is going in exactly that direction, and I have a list of authors who are sort of working on it. They in their papers they discuss questions of exactly that sort, and if people want specific references, I can do that later. But we can go back to the question: what unifies geometry? What allows it to connect with other fields? Well, it could be common language, or compatible structures, or moduli, that is, say, parameterized families of structures, where the specific structures characterized or classified by that parameterized family is held together in an amazingly rigid way by the usually richer structure of the modular space than the initial structure. Or metaphors, analogies, and they can be powerful. The American philosopher Ralph Waldo Emerson has his view of the subject. He says, man is an analogist and studies relations in all objects. Okay, I wanted to make a kind of an ad hoc collection of words which might talk about the way in which one binds subjects. So ties, analogies, links, and bridges. A tie is going to be sort of the weakest thing. It simply just brings things together in disparate fields. An analogy is something more. It suggests that there is a kind of resonance or similarity in their structure. A link is some sort of real joining, and a bridge actually allows you to prove things from one subject to another. So, for example, Bernoulli numbers I think of as an amazing tie between 6 different subjects, between modular forms, for example, and it begins the discussion of interpolation of modular forms via Bernoulli numbers. Number theory and analysis, the Riemann zeta function with Bernoulli numbers as a center, and differential topology and homotopy theory. For example, the relationship between differential topology and homotopy theory just can be illustrated by the marvelous classical curvaire Milner formula, which talks about the numerator and denominator of Bernoulli numbers. So you take the even Bernoulli numbers, B2k divided by 2k, write it in lowest terms as numerator and denominator, and lo, the numerator just gives you the number of different differential structures on the sphere of the relevant dimension. The denominator goes in a completely different way. It tells you the size of the co-kernel of the J homomorphism in the stable homotopy group of spheres, again, in the relevant dimension. So now in my abstract, I take a comment of André Weil, nothing is more fruitful, all mathematicians know it, than those obscure analogies, those disturbing reflections of one theory and another, those furtive caresses, those inexplicable discords. And then comes the blue part of this comment, which I hate. I absolutely hate, by the way. The day comes when the illusion dissolves. The yoke theories reveal their common source before disappearing, one achieves knowledge and indifference at the same time. Nonsense, I think. Not indifference. There are metaphorical bridges begun in ancient mathematics that connect things that we are sort of as excited about now as we were, in ancient times. Geometry is algebra. So there is a bridge between geometry and algebra. But there were people who said no. For example, Aristotle in his posterior analytics says, one cannot demonstrate a geometrical problem by means of arithmetic. How wrong he was. And René Descartes made it perfectly clear that he was wrong. Descartes said at one point in his writings, I would borrow the best of geometry and of algebra and correct all the faults of the one by the other. And of course, he was turning algebra and geometry into a single subject by a true synthesis. And we have algebraic geometry. Now, here's just a rapid view of the evolution in the past century of that subject. I'm starting it with Severi, with the Italian school. And as I write here, the temper of that school was total non-rigor. They're focused on the geometry of algebraic geometry as their primary source of intuition. And they're perfectly happy to assume that the objects they were dealing with could be put in general position, giving no formal justification for this. And there were lots of mistakes in Italian algebraic geometry. For example, Severi's famous Appendix F, which, anyway, that's another subject. But the move towards focusing on algebra and algebraic geometry was done fairly soon in this century, and it was successfully done by Zariski and others, including the earlier work of Krull and Emmy Noether and Van der Verden and others. And what they did was they rigorously, they rigorized, if you wish, the intuitions of the Italians by focusing on fields of rational functions, by focusing on the algebraic side of their subject. I don't know how many people in this conference have read André Weil's Foundations of Algebraic Geometry. When I was young, people did read it. It's hard to read. It's sort of, and at exactly the same time, I think, I say approximately, but exactly the same time, there were really ultra algebraic approaches to the subject. For example, Chevalet's Introduction to the Theory of Algebraic Functions of One Variable. Has anybody in this conference ever read this book? It doesn't have a picture. It's talking about curves, after all, but it has no picture, no pictorial language. It's just fields and extensions of fields. It's sort of like a novel of Perec that has no ease in it. I mean, it's just trying to keep geometry at bay. That is to say, in this book of Chevalet's, but in contrast, in Chevalet's seminar in Paris in 57, 58, I was there. He developed his ideas about the foundations of algebraic geometry, a kind of a proto-scheme theoretic view. And it was not about fields at all. It was also about rings, commutative rings, and was a precursor to Grothendieck. And Grothendieck, of course, provided a unification even more striking, allowing for what we nowadays call arithmetic algebraic geometry, or and even sort of more inclusively arithmetic and automorphic algebraic geometry, which includes automorphic representations. Okay. So so what ties these things together? I think L functions does the tying together. I mean, the connection between L functions and automorphic representations we've seen in a lot in this conference. The connections with arithmetic algebraic geometry, well, these L functions are characteristic polynomials or series connected very often to étale cohomology of algebraic varieties, and the direct connection with algebraic number theory is clear. So there are two interlacing grand programs, which we've heard lots of talk about today. There's the Langlands program, where the tie, I say, is between automorphic representations and Galois representations. And there are main conjectures. And there's a real bridge between Galois representations and various arithmetic cohomological invariants, like Selmer groups and Mordell-Weil groups. The bridge is Euler systems. And Euler systems are specifically constellations, very organized constellations of algebraic cycles that really allow you to prove theorems, that is, say, linking the two sides of that bridge. Okay, now I also said in the abstract that I wanted to talk about the connection between knots and primes. And this is getting to the exercise that I felt obliged to make with Olivia's invitation for me to give a talk in this conference. So I want to talk about, and I'm going to focus on this for the rest of the hour, knots in three manifolds and its relationship to primes of number fields, or if you want, knots in the three-dimensional sphere and ordinary primes. It's an analogy that unites topological structures with arithmetic structures. And nowadays, more broadly, it also is the way of tying together geometry and physics. So there's a kind of triumvirate there. And if you want a really beautiful, beautiful discussion of just this triumvirate, take a look at the video lecture by Morishita called Knots and Primes. Now, if we're going to talk about knots as primes, I want to talk a little bit about Z, or spec Z, as the three-dimensional sphere. Now you see in the slide, I make a union of spec Z with the pointed infinity. I'm sort of compactifying the spec Z. Now for experts, they'll know that the reason why I'm doing this is I'm constricting control on étale coverings of spec Z in terms of how real Archimedean primes split or don't split. But this is don't worry about this if you're not happy about it, because all it's there. The reason why it's there is it's going to get rid of a few Z mod 2s in cohomology. Okay. Now that we've given this script S as a definition, or almost a definition, the first thing to say is that it's simply connected. It's simply connected simply because the ring of integers Z has the property that there are no everywhere unramified there are no unramified extensions of Z. Now, the cohomology of this S, one needs a bit of class field theory, and it's nicely done if it's also reformulated in terms of flat and flat cohomology as well. So here's the cohomology of our S, our putative three-dimensional sphere, with coefficients in the multiplicative group, GM. So the things to look at first is that when I is 1 or 2, the cohomology is 0. That is, say, as far as GM is concerned, our S, our three-dimensional sphere scheme here, is 2 connected, is simply connected, 2 connected. It's of dimension 3 because the cohomology vanishes for in dimensions greater than 3. And here's a Q mod Z in dimension 3. This is perfect for perfect dualities, which actually are the case. The easiest way to describe a setup where you have perfect duality, which I want to think of as a Poincare duality, is you take a finite flat group scheme and you let F star be its dual. It's the group scheme that you get by taking the scheme Hom of F into GM. And this is a really nice duality between F and F star. They have the same rank. And also, if you use the natural tensor product F tensor F star mapping to GM, given by the definition of F star, you get that the cup product, you get a map from the ith cohomology of F and the 3 minus ith tensored with the 3 minus ith cohomology of F star into H3, which is Q mod Z, and that's a perfect pairing of cohomology groups. Okay. And you can also replace, do it with X as well. And this is a similar perfect pairing where I've, instead of dealing with a GM, which is a smooth group scheme, I'm dealing now with mu n, which is the kernel of multiplication by n in GM. That is, say, the finite flat group scheme given by nth roots of unity. So things work perfectly well, allowing us to think of S as morally two-connected and as enjoying a three-dimensional sort of Poincare duality, but it's oriented by the coefficient sheaf Gm. It also contains, and I put Chebatarov in red there, a family of disjoint knots. But since I'm thinking of knots as primes, my disjoint knots are 2, 3, 5, 7, 11, and 13, and so on. So what is a knot as a prime? The knot P. So if P is a prime, we can consider a reduction mod P. So Z goes to Z mod P, Z, which is the prime field, Fp. If I call spec Fp script K sub P, the script K already suggesting that it's a knot. It's in this surjection embeds script K P, our knot, as our prime as knot, into script S, our scheme as a three-dimensional sphere. And Kp is, of course, what I want to call the knot attached to a prime P. And of course, we have the Fp is contained in Fp bar. The Galois group is Z hat. It's a beautiful setup, of course, where we have natural automorphism of Fp bar, the Frobenius, which generates this topological group, Z hat. And we can write it on the scheme theoretic level as well, where we have the spec Fp bar as a covering space of spec Fp. Spec Fp bar is, from, as I say here, from the étale homotopic perspective, it's contractible. And the deck transformations here are Z hat. So we can think of our knot Kp as homotopically a Kz hat one space. And once before, as I say, we get into specifics, here are our corresponding objects. Let us say on the topological side, we have we can think of knots capital K. I'm thinking of it as Roman K here, as one spheres as S1. The fundamental group being Z, and our knot prime, whose fundamental group is Z hat, and the analogy is between blue and red here. So for the topologist, we can make if we think of a knot in S3, we can make a tubular neighborhood of the knot. It's not going to matter what tubular neighborhood you make, and as long as it's reasonable, in which case you can decompose the three-dimensional sphere as the tubular neighborhood union the complement or the closure of the complement of the tubular neighborhood, which I'm calling xk. Okay, so here's our tubular neighborhood, and the boundary of that xk, which is the intersection of xk and the tubular neighborhood, is also the boundary of the tubular neighborhood, which is the torus boundary of both manifolds, xk and nk. Of course, the torus boundary will have two natural cycles to generate things. The M I'm calling M the meridional cycle, and L the radial cycle. So L is this radial loop. It's sort of the shadow of the knot. The meridional loop is nicely defined up to homotopy. And especially if I'm assuming that K is an oriented knot, let's do that. It's an actual loop, perfectly well defined, even in its orientation. And sort of ditto for the radial loop, except it's defined only up to the ambiguity of adding a multiple of the meridional knot. So there's the homotopy type of this knot complement. I called it XK a minute ago, which is the complement. Well, it's not quite this, it's the closure of the complement of S3 minus NK. But this or its closure, both of them are homotopic to the actual complement of the knot, S3 minus K, sitting in S3. And there is this marvelous Gordon-Luecker theorem, which tells us that if you want the homeomorphy type of S3 minus K, and even less than that, completely determines the knot up to isotopy in S3. At least if the knot is oriented and you keep orientations in mind. The cohomology of the knot complement, well, one has Alexander duality, and it establishes a Z duality between H1 of this of the complement of the knot and H lower 2 of the relative relative homology H lower 2 of the 3-sphere relative to the knot, which itself is Z. And so therefore we have a canonical isomorphism between the cohomology of the complement of the knot and Z. And that tells us, as all kids who study knot theory know, that all the finite abelian covering spaces of S3 branched at the knot, but unramified outside it, have cyclic groups of deck transformations. The cyclic groups have canonical compatible generators. And we can consider X-ab the maximal abelian covering space of XK, which has a group of deck transformations. I'll call it gamma, canonically isomorphic to Z. There's the arithmeticians complement of the knot, which follows exactly the same story. That is to say, you join the inverse of P to make the ring Z brackets 1 over P. And the complement of this script KP, that is spec FP, in our arithmetic 3-sphere S, is given simply by spec of Z brackets 1 over P. And there it is. So you have a topologist picture and an arithmetician's picture, and they look exactly the same. You have the boundary of the tubular neighborhood to the tubular neighborhood, embedding in S3. You have the boundary of the tubular neighborhood going to the complement, if you wish, and one has exactly the same story here. The thing that corresponds to the torus is spec QP. To repeat this, there is a kind of a local. There's a local story here where the blue is the topological and the red is the algebraic. And wait, where did I go? Yeah. Hold on. Okay. And we have the global analogy similarly. where the knot K is in S3 corresponds to this picture. And this is going to allow us to frame possible statistical analogs. We have fundamental groups mapping to homology groups in analogy, allowing us to produce maximal abelian unramified extensions in analogy. So I'm going to write S3 minus K infinity to be the maximal abelian extension unramified outside K of S3 minus K, and ditto for spec Z. With spec Z, the maximal unramified abelian extension over spec Z is given by the p power roots of unity. And so there's the picture. And that's an invitation to compare the Alexander polynomial, which is the characteristic polynomial of the action of gamma on the relevant cohomology of S3 minus K infinity, of that guy on the left, and with the Iwasawa polynomial, the characteristic polynomial of the action of gamma on the relevant cohomology of the right-hand side. It's natural to make the comparison. And once you make the comparison, you open up your collection of questions to how can we continue that comparison with the things that are connected on the topological side to the Alexander polynomial, and the things that are connected on the arithmetic side to the Iwasawa polynomial. So, for example, the Alexander polynomial is a specialization of the Humphreys polynomial, and that, of course, is also connected to the Jones polynomial, which is also determines the Alexander polynomial. What corresponding objects are there on the arithmetic side? And on the arithmetic side, we have the main conjecture that attaches a connection, sort of almost an equality between the Iwasawa polynomial and the p-adic L function. That is to say, the p-adic L function is, by the main conjecture, equal to the p-adic Iwasawa polynomial times a p-adic unit. Is there sort of a fine structure for the Alexander polynomial? And of course, the p-adic L function is connected to the classical L function. So what happens on the topological side? So we've gotten back to the question I asked earlier: what is the arithmetic algebraic interpretation of the Jones polynomial? And now I want to give a sort of a number of comments on comparisons and differences. Well, first, knots. There is the unknot in knot theory. That is, say, the straight circle sitting in S3. You can determine whether you're unknotted or not just by taking the fundamental group, and you can ask, is that fundamental group abelian? But even from that perspective, every prime is knotted. That is, say, the fundamental group of any of the complement in S of Kp for any prime is not abelian. And there's a serious distinction between knots and primes that has to do with what's called wild inertia, and a structure that's of absolutely crucial importance in number theory. But there's no corresponding complexity in knot theory. There is, on the other hand, a duality in the structure of the Alexander polynomial. It's invariant to the t goes to t inverse. But I say there's nothing like that in the Iwasawa polynomials. There is something, and we can discuss it if people are interested. But it's not a straight duality as the Alexander polynomial. And of course, we can discuss links. A link would be a pair KL of knots, which are disjoint, corresponding to, on the arithmetic side, a pair PQ of primes disjoint. Now, once you have such a link, for the pair PQ corresponding to primes, we have quadratic reciprocity. That is, say, if you ask the question, is P a square mod Q? That can be answered in terms of very elementary data by the question, is Q a square mod P? Ditto for skew symmetry of linking numbers in knot theory. That is, say, the natural way to make a linking number is to take two knots, L and K, and form a Seifert manifold around one of them, say around L, and consider the intersection of K with that Seifert manifold, and you get a number. And you could do the same by putting a Seifert manifold around K and considering the intersection with L, and you get another number, and those two numbers are the negatives of one another. So that's sort of like quadratic reciprocity, and it's proved exactly the same way, given our it's proved the same way in a certain sense. And you could even go, instead of taking two primes, you can take triples of primes and ask, is there some relationship between triples of primes and Borromean rings? And the answer is yes. There's a classical invariant of triples of primes called the Rede invariant, which, if you put in a chromological perspective, turns out to be a Massey triple product, which is exactly the sort of thing on the topological side that produce what are called Milner invariants. The question always given these invariants is, can you untangle the three links of, the three knots in the triple link? But I want to make, now comes the exercise, and I think I have time for it. The exercise that I felt would be worth pursuing, given that the question is unification, unifying themes in geometry. So I'm going to make a sort of a more specific connection between primes and knots. And it seems to me that this is the right connection. That is, say, I want to make the analogy sort of more precise between primes and hyperbolic knots. Now, a hyperbolic knot or a link is a knot or link whose complement is a hyperbolic manifold. Let us say a Riemann manifold with constant negative curvature -1, and complete in that Riemannian metric, and of finite volume. The finite volume is important for us because I'm going to call that volume of that hyperbolic knot, that's the complement of K, I'll call that the volume of K. And one might want to make that volume somehow analogous to the size of P. I think it's rather than the absolute value of P, it'd be more like the log of P. And I want to do this because I want to ask norm size statistic and Cherepanov questions. So let's fix a knot K. And for any positive number x, I'm going to let this script pk of x be the set of isomorphism classes of links, I'll call them lambda, in S3 that are of the form, the link is L disjoint union with K, okay, where L is some oriented knot disjoint from K and is such that L disjoint union with K is a hyperbolic link of volume less than or equal to X. So that is, say, the complement of L union K in S3 is a hyperbolic manifold of finite volume and volume less than or equal to X. So that's my set, pk of X. So now we can begin to ask a certain amount of, if you wish, the corresponding analytic number theoretic questions, but on the topological side of things. Okay, so here's a Chebatarov type question. First, by results of Thurston, these are amazing results, by the way. There's a limit value, x bar, such that for any x less than that limit value, this set is finite. That is, say, isomorphism classes of those hyperbolic links of volume less than x is finite. And Gromov has a very beautiful Bourbaki seminar article giving the gist of this. The title is Hyperbolic Manifolds according to Thurston and Jorgensen. Okay, so noting that any such link, for any such link, the oriented knot L sits in the complement of K in S3, and so determines, it's an oriented knot after all, it determines a conjugacy class, and I want to call it phi lambda, of elements in the fundamental group of the knot. It just sits there in the complement, and it's a loop, and so therefore it doesn't produce an actual element in pi 1 of K, because you have to sort of connect it to the base point, and the connection to the base point will, if the connection to the base point changes, you'll be changing that element of pi 1 by something conjugate. But it does produce a whole conjugacy class of elements. And the reason why I call it phi lambda is because it is absolutely the analog of Frobenius. Frobenius attached to the knot L, well, given that we're working in the complement of K. So it's natural to ask essentially almost any analytic number theoretic question that we have in arithmetic to ask it in this context of knot theory. So there's the question. For any normal subgroup, well, it doesn't have to be normal, of course, but anyway, for any normal subgroup in the knot group of K and any conjugacy class in the quotient group, pi K over H, I should say, is it the case that the number of Frobenius elements for lambda less than lambda and pk of x, the number of Frobenius elements that map to that conjugacy class divided by the number of links of volume less than x, in other words, the percentage of these, the ratio of these classes, is it the case that as x tends to this limit value x bar, that this ratio tends to the analog of what it would tend to if we were in arithmetic? That is to say, the size of the conjugacy class divided by the order of the group. this is a question. I wonder whether it has been well, so I wonder whether we're in a position to be able to pursue it. I felt that this is first a really interesting way of trying to make a connection between an sort of easy, I would say, easily graspable connection between arithmetic and topology, and we might go further. The minute you have that sort of situation where the phi lambdas, the topological versions of the Frobenius elements, are nicely situated in the global knot group, you can ask interesting questions about eigenvarieties, generalize Iwasawa theory for knots, and introduce the mechanism of Heck algebras in the hyperbolic context. So thanks for offering me the opportunity to raise these questions. That's it.